All right, so now we're going to look at the other couple processes that are involved in urine formation. These ones, honestly, a little bit more straightforward. We'll talk a little bit of depth about some of these different metabolites and how they're reabsorbed. Again, just getting more of the basic ideas of it. I don't know that I'm going to try to give you an essay that says, explain to me how potassium is reabsorbed versus sodium or something else like that. But just trying to get at the processes involved in reabsorbing a number of these things here, as well as we'll get into tubular secretion at the end. Again, we make this filtrate, and what we have to do is then modify what's in it. So stuff that we don't want to become part of the urine that we want to reabsorb, we need to get that stuff back out of the filtrate, and things that don't end up in the filtrate that we may want to get rid of, or things we want to secrete in order to balance out other systems we might want to secrete in there. And that is where these other two processes get involved. So like it says, there's some substances reabsorbed from the tubular fluids back into the blood, and some stuff that is not part of the filtrate originally, we can secrete into that. Again, whatever is in these tubules by the end of this, as they're starting to move their way down to the collecting duct in the renal papilla, is going to become urine at that point. So like I said, a lot of this is about modifying what is in that filtrate. Main thing is we're going to have a few different processes where the stuff is going to be moving through there. So we can kind of have stuff go, or sometimes diffusion or osmosis, traveling between cells. That would be the idea of paracellular transport. Substances moving between the epithelial cells, where transcellular transport is basically you're moving into the cell and then out of the cell on the other side. So that's traveling through the epithelial cells, not between them. Again, proteins in these different membranes can deal with a lot of this, and that's what's a lot of times control the movement of these things here. Those peritubular capillaries are surrounding these. They do not have a lot of blood pressure because we've pushed a lot of that filtrate out already. Because of that, they have a much higher oncotic pressure, and a lot of those bulk flow mechanisms of osmosis trying to move back into those blood vessels is going to be happening, and sometimes this can pull some stuff along with it. And again, as I was saying before, most of this is happening in that proximal convoluted tubule. We'll see there is some other reabsorption that can happen in a few other places, but again, the one spot where we see those microvilli is in those proximal convoluted tubules, which we know that is always about trying to get more surface area for more absorption to be able to take place. This is kind of showing that idea right here, where you have the blood vessel. So again, that paracellular transport in between them. Where transcellular, you're going to have pumps on the luminal as well as the basal surface to move these things through the cells. And again, those blood vessels are kind of set up to be taking substances into them because of their low hydrostatic pressure and high colloid osmotic pressure. They're going to be trying to pull water into them. And because of that, some of these substances are going to be able to be transported in rather easily. With any substance, a lot of times we're going to talk about the ability of these tubules to actually be able to reabsorb them. So at some level, there is a maximum that we can reabsorb, a maximum amount. And if we were doing more than that, I mean, think about it like a pump, a sump pump or something else like that. You have fluid going into this area that is then pumping this fluid out. If you get more fluid than the pump can pump, you are going to start building up that fluid, and it's going to flood your basement type of thing. It's kind of the same idea here with the transport mechanisms on these reabsorptive ideas here. There is a certain amount of reabsorptive capacity that we have. That is at transport maximum. So we can, for example, glucose, 320 milligrams per minute, you can reabsorb. If there is more glucose than that in the filtrate, it means we can only absorb that amount. Anything in excess of that is going to become part of the urine. This is actually what happens with diabetes, for example. You're getting your blood glucose levels are getting so high, we try to reabsorb as much as we can, but because it's actually basically saturating these transport mechanisms, anything that's in excess of that maximum amount, that transport maximum, is going to end up in the urine, and that's how you end up with glucose in your urine with different types of diabetes. So that renal threshold is that maximum concentration that stuff can be in the urine without actually, maximum amount of stuff, that threshold level that it can be in the plasma without it ending up in the urine. Anything above that renal threshold, if you have a higher concentration of that in the plasma, it means it's also going to end up in the urine. And again, with diabetes, that's what it's kind of talking about here. If you start getting blood glucose levels of a high enough level, it is going to end up in that filtrate, and you're not going to be able to reabsorb all of it. The other thing that does to us, though, and if you may have heard that sometimes one of the signals of early diabetes is, before you maybe know that you have it, is you have increased urination. What starts happening is metabolite, it can be an osmotic gradient. So glucose that's not normally in this filtrate, because we absorb all of it, all of a sudden is there, that is setting up an osmotic gradient to draw water into those tubules. And if we draw more water into those tubules, you're going to have more urine loss. So that's one of the things that we can see happen with diabetes. Sometimes when you get a metabolite that isn't there, it sets up an osmotic gradient and causes us to lose more water than we would otherwise. So as I was saying, certain substances we are going to reabsorb 100%. Certain nutrients and plasma proteins we're definitely going to be doing that with. Again, things like glucose completely reabsorbed in that proximal convoluted tubule. Again, each nutrient, though, is going to have its own transport proteins and therefore its own renal threshold, its own transport maximum levels that we can do with it. Like I said, glucose is done by transporter proteins. It's sodium glucose symporter. We're going to use that energy from sodium to move glucose out of the tubule by secondary active transport through into the cell and then out the basolateral membrane. And again, all that is returned to the peritubular capillaries and therefore the bloodstream. And in normal, healthy individuals, we should not see any glucose ending up in the urine. And again, showing you that idea right here, using that sodium glucose symporter, we get it into the cell and then have a basolateral one here, pump that is moving that into that interstitial fluid, which will get taken back into the capillary. Most protein, again, not freely filtered. Some small and medium-sized ones can end up in the filtrate. Again, we use transporter proteins and penocytosis, taking some of this fluid to take those proteins back out of here. And again, those amino acids, for the most part, should be fully reabsorbed. We might see a small amount in the urine, but no noticeable levels that much. Very below 1%, below, it's 0.0 something or other. Sodium reabsorption, we reabsorb a lot of this, but we're still going to have a decent amount end up in the urine. Sodium, we're going to see it's about 98 to 100%, depending upon other signals that are going on here. We actually reabsorb this through a number of different parts, mainly in the proximal convoluted tubule, but we'll see some in the loop of Henle and some of the other areas as well. We're going to see inside the tubule cells, it's not particularly high. It's high within the lumen and high in the interstitial fluid, but we are actually kind of pumping it through those cells, and those cells don't keep a particularly high level of sodium in those peritubular cells. And again, we have sodium-potassium pumps lining these membranes. We're going to continue to pump this out of the interstitial fluid where it can be taken up into those peritubular capillaries. Again, we've talked a little bit about it already. We'll get a little bit more into the mechanism of it, but aldosterone and atrial natriuretic peptide, we know aldosterone increases sodium reabsorption and brings water along with that. Atrial natriuretic peptide was working in the opposite direction. It decreases sodium reabsorption, and because of that, increases water loss and urine formation. So those are some examples of ways that certain metabolites can be actually modified based on hormonal signals. Aldosterone, like I said, adrenal cortex, it is going to stimulate production of more sodium channels and more sodium-potassium pumps. What that does is if we have more of those, we're going to get more of those in those cells lining the tubules, we're going to increase sodium reabsorption because we have more pumps to pump it. Therefore, our threshold can be higher. Our transport maximum can be higher. Again, water tends to follow those electrolytes. So again, they create an osmotic gradient and water will follow that. Atrial natriuretic peptide is actually going to do the opposite of this. It inhibits the release of aldosterone, inhibits reabsorption of sodium, means it's staying in that filtrate, which means more of the water stays in that filtrate. And we're going to get increased filtration rates and we're going to increase urine formation. And again, this is just kind of the figure showing this. we're pumping a decent amount out, but like I said, we are still going to lose some sodium generally in the urine. And again, showing you that in the proximal convoluted tubule, it is more sodium channels and pumps, and sodium flow because it's higher in the tubular fluid by diffusing into that cell, and then we are pumping it out to the interstitial fluid. We're going to see as we get to these distal convoluted tubules and collecting ducts, we can kind of regulate this a little bit with these production of these channels or production of these sodium potassium pumps, which can increase the reabsorption under certain conditions. Again, water reabsorption, it's happening really throughout these tubule systems, or it can be depending on, again, hormonal signals. It is, again, osmosis, mainly this paracellular transport between the cells. We are going to see some water transport proteins called aquaporins, these channels that are there. Again, we've already said 180 liters of filtrate on average a day, which is 45 gallons, is how much filtrate we generate. We urinate on average a day of about 1.5 liters, which is less than half a gallon. So we make 45 gallons of filtrate. We excrete less than half a gallon of that. So we are reabsorbing the vast majority of water out of our filtrate. Again, depending on where we're at, most of this is reabsorbed in the proximal convoluted tubules. Lots of aquaporins here, follows that sodium reuptake that we're doing. The water is just following it based on osmotic gradients. As we get into the nephron loop, it's about 10% more of the water is filtered there. We're going to see when we'll talk about this in the next one, we actually have differing permeabilities on the ascending and descending loops, so of salt and water, and we can use that to kind of get what's called a countercurrent mechanism in place, which allows us to pull more and more water out as we go down. It's not a large amount of the water, but it is helping us get some more of that water back out. And then when we get to the distal convoluted tubule and collecting ducts, due to these changes in those sodium gradients, if we have aquaporins present due to aldosterone or antidiuretic hormone, we can actually reabsorb even more water there when those signals are present. So antidiuretic hormone binds to what are called principal cells and causes vesicles that have these water channels, these aquaporins, to go to the membrane. If we have more aquaporins, we can reabsorb more water. And again, there is an osmotic gradient there that we'll see on the next presentation here that is allowing this to happen. Kidneys are an interesting one in that if you actually look at the kidney from the cortex, as you go further down in the medulla, you have least amount of salt at the surface, and the further you get into that, the deeper you get into the kidney, the more salty it becomes. Kidney is actually an interesting one. If you were to freeze one, it will actually thaw inside out because the salt concentration on the interior is so much higher. That water will unfreeze first. And again, if we have these aquaporins, water will be reabsorbed out there. And again, it's under that ADH, and again, aldosterone is going to be these couple of things that can really do this. This is what we refer to as facultative water reabsorption, in that if the signals are happening, it will occur. But unlike what's happening in the proximal convoluted tubule, that's always going to be happening. This one, we can hormonally turn it on, turn it off. So antidiuretic hormone we talked about is a posterior pituitary hormone. It is going to increase water reabsorption. One of those things that we can really reduce our water volume in the urine, can help us to really concentrate it. If we have higher levels of this, it will cause you to reabsorb more water and really concentrate your urine. With less of it, the urine is less concentrated. Because of that, we can see really wide ranges in how concentrated the urine and waste products within that urine can be, depending upon the level of water reabsorption that we need to do. So it's also in salt content or sodium content as well. It can be, like it says there, from 1200 milliosmolar to 50 milliosmolar. That's quite a wide range. And again, dependent upon these signals and what they're doing to cause more or less water reabsorption. And this is showing you those aquaporins and the ability of this to get out of that tubular fluid and back into the bloodstream. Again, more ADH, more aldosterone is going to increase this process. Potassium, it really can kind of go either way. Sodium, we reabsorb most of it. Water, like I said, a lot of these metabolites we talked about, we were doing the vast majority is being reabsorbed. We can sometimes even actually have a net secretion of potassium. So on average, it's about 60 to 80% of potassium is reabsorbed from this tubular fluid, but again, it's going to depend upon signals and gradients and concentrations in that plasma in terms of which way this is going to be going. Sodium reabsorbed, like I said, there across the luminal membrane with water following. Potassium is kind of dependent on the sodium movement. So potassium, though, is going to move down its concentration gradient in a paracellular between those cells route. And again, that sodium moving creates a gradient that this is going to follow. We have some of this taking place in that thick segment of the loop of Henle. And again, if we get to the tail end here, if we need to get rid of more of this, we will actually can sometimes get a net secretion. Again, potassium is one of these ones that's really dependent upon the aldosterone levels. If you have high aldosterone, it causes you to reabsorb more sodium and excrete more potassium. Again, this is the one I would say I'm not going to get too deep on this, especially this one, just because it's really entirely dependent upon a lot of the signals that you're getting. So we get a good chunk of it in that proximal convoluted tubule, some in the distal convoluted tubule, and again, depending upon sodium levels and other things like that, what's happening in that collecting duct can kind of depend upon aldosterone levels. Calcium and phosphates, again, going to depend a little bit somewhat on signal. Calcium and phosphates, a lot of this is going to be reabsorbed. So like it says here, about 60% of it that's in the blood becomes part of the filtrate, and like it says, 90 to 95% of that is filtered as blood passes through the glomerular capillaries. Again, what's going to happen with these ones is highly dependent upon, again, our signals from stuff we've actually talked about before, back in the bone chapter. If we're having parathyroid hormone, that was something that was going to increase blood calcium levels. One of the ways to do that is to make sure we don't excrete much calcium, so we reabsorb more of it. So parathyroid hormone is actually going to inhibit phosphate reabsorption, but stimulates calcium reabsorption in the distal convoluted tubule, which means we get more calcium back to the bloodstream because it can't go out in the urine as calcium phosphate, and that will increase blood calcium levels. Calcitonin, again, inhibits that response. When we start looking at some of these other ions, so bicarbonate ions, hydrogen ions, and kind of body pH. Bicarbonate ions can get moved freely into the filtrate. We have to reabsorb some of this, otherwise our blood would be too acidic because only small amounts of those hydrogen ions are filtered due to their charge. So we generally reabsorb about 80 to 90% of our bicarbonate ions from that tubular fluid. And then the remaining part of that, and that would be in the proximal convoluted tubule, the remaining part of this is taken up in that ascending limb of the loop of Henle. One of the things we can see here with the secretion on this stuff here is, depending on the blood pH, this, like I said before, the kidneys are one of our physiologic regulators of blood pH along with the respiratory system. So pH of the urine and blood regulated by either secretion or reabsorption of some of these things here. So if blood is too acidic, we are going to reabsorb a lot more of that bicarbonate ion and we're actually going to excrete hydrogen ions through those intercalated cells in the collecting ducts to actually bring the blood pH up and let the urine pH get nice and low by taking alkaline out of the urine and putting acid into it. If the blood is too alkaline, we actually have the opposite happen. We secrete those bicarbonate ions and reabsorb hydrogen ions to bring that blood pH down and let the urine pH go up. And one of the things we can see is sometimes this is also very dependent upon your diet. There is what we call alkaline and basic diet, alkaline and acidic diets, depending on levels of vegetables and meats and other stuff like that you tend to eat. You can tweak this a little bit. Kind of a fad diet thing, but it's something you can actually take a look at. And again, just kind of showing you where we reabsorb most of this stuff here. And again, when we get to that collecting duct, we have regulated reabsorption or secretion depending upon what we need to do for homeostasis. And again, this is just showing you the idea how we reabsorb it, how we can secrete the hydrogen ions, reabsorb the bicarbonate ion if the blood is too acidic. Again, showing you that right here. So really the last stuff that we'll look at on this one is we'll take a little bit of a look at a few more things with this reabsorption and secretion, and then we will move on to kind of the different parts of the urinary system, which is those ureters and the bladder and the urethra, which again, that's basically one show. You can see the kidneys have been like 6 shows here. That'll be one. So I'll see you next time.